So I'm doing a PhD in philosophy, logic, language, and computation, jointly between St. Andrews and the ILLC. I love that we've talked about most of those things, and especially mostly realizing, what is logic is a good question. Hard to answer. I don't really know. What's philosophy? Good question. Very hard to answer, maybe even. I don't really know. What's language? Well, I'm also not quite sure. And computation, as we've heard today, also kind of tricky question and not necessarily with a straightforward answer. My PhD is supposed to combine all four of them. And this is the groundwork of the whole project. And then it kind of branches out into kind of sub-projects. So there is a project that tries to automatize what I'm doing. There is a kind of sub-project that tries to dabble a bit in natural language processing and applications of what I'm doing. But the core work is really inner logical. I deal with n-sided sequence calculi in the core part of the PhD. And then I also try to publish in generalist philosophy journals. So I try to dance at many weddings at once. Let's see if anybody will be happy with me when it comes to the job market afterwards. But that's always a tricky question. This is just the centerpiece, and it kind of has a little bit of everything, but at the same time, absolutely nothing of any of the four. Cool. I work in proof-theoretic semantics. That's the short story. And in proof-theoretic semantics, you're interested in questions of meaning, and specifically, you're often interested in the connectives. Let's focus on those here, and let's specifically only focus on the conditional, and let's look at two different conditional statements, if A then B, and if A then B, one expressed with the right arrow and one expressed with the horseshoe. And we're going to ask, do those two expressions mean the same? And as we've heard before, in the research program of inferentialism, the standard answer to this question is, well, when do we use them the same? We use them the same if we use them the same when we make inferences with it. And then specifically, the proof-theoretic semantics research program could be seen as a sub-discipline within the inferentialist research program, where people say, well, how do we see our inferential use? Well, when we do proofs, we use the connectives according to their proof rules, right? So in order to figure out what's the inferential use of our connectives, look at the proof rules. And they will tell you. But then the question is kind of, when are those two connectives governed by the same proof rules? So when are two sets of proof rules the same? And that's a question that very few proof-theoretic semanticists address in this specific formulation. I think most people don't care about it. They're more interested in actually looking at the proofs themselves. But if you ask this question, like, what exactly about the rules makes them identical, and you get into the idea of like a theory of identity of rules, there's little discourse. One person who has talked about it and who seems to be the standard for a lot of people in the literature still is Greg Restore. I normally would draw a little doodle of Greg Restore, but I'm so tired I might make it offensive, so I'm going to leave it be. It would be, short beard, because in a second I'll have a short beard and relatively long hair, and in a second we'll have very short hair and long beard, as you'll see, which would be the second doodle. I'm just going to omit them. And according to Greg, the idea is, well, two rules have the same meaning if they share the active formulae and the principal formulae, which are called the active components in this presentation of their proof rules. So what you get, for instance, is you get here, these are the additive proof rules for intuitionistic right arrow in one formulation, LJ, and here you have the dual of it, dual intuitionistic conditional. And look at this, all of the highlighted formulae, the active formulae and the principal formulae, they're in the same position relative to the sequence symbol. They've got the same active components, so they should have the same meaning. And as you know, right, you could tell this story with quite a few different examples. So you could have, the ones on the left were actually multiplicative and the ones on the right are additive. In a way, I'm conflating two things, so I'm going to drizzle them apart. For this presentation, for this audience, it was great to conflate two things. I'm going to not conflate them. So one interesting effect that you get here, so this is just the scaffold of the rules, and I think I've only focused on, no, I've actually looked at both rules here, is that you have, so the left rules, this is the scaffolding, right? These are the active formulae of our rules. And then you get on the left and on the right, I'm just going to use the right arrow symbol for this, right? And then these are the active formulae, they stay the same. Everything that we can formulate out of the scaffold would then be having the same meaning, would have the same proof rules. And so we could make them, let's say, we make them additive, right? Then you get this. But you could also multiply the contexts. You get this out of this. These are both classical. We've seen classical rules before. Right? In order to make this one additive, you would then need to split the A and the B. So you would have instead two rules. You would have this one and that one, and you could use either or, and from both of them get them on the right. If you don't believe me, check the truth table, right? That works. These would give us the additive rules, and then you add the additive context, and you can play around. You can also restrict the set theoretic properties of the derivability relation, right? You restrict yourself to at most one formula on the right, but leave the left unrestricted. If these are multi-sets, let's just assume for now. I like to work with lists because I like to be very kind of nitty-gritty, conservative with these things. You could restrict the other way around. You know, you end up with the dual interstinstic connectives. You could restrict to just one instance. You could restrict to exactly one on the right. You know, Tolstoy and Schwichtenberg's minimal logic. You could keep the restrictions the same, but you could actually be dealing with those in calculi that don't have weakening, right? And you've got all of the relevant logic calculi. You've got LKR, LJR, LDJR, LLR, LMR, you know, all of those logics, just the relevant logic version under one reading. I think Ferrari and Olandelli defined those calculi. All right. That's the long story, but in short is all of those things have the same active components, so the same proof rules and have the same inferential use. The problem is now you do proofs with them, and you don't operate in this fully strong, full structural strength calculus where you've got, you know, contraction, weakening, transitivity, reflexivity available, and you will quickly see you get very different proofs. You get very different ways to use them in proofs. So here, this is mostly what you see here, even though it conflates the dual interstinstic distinction with the additive multiplicative distinction. If you add these rules each to a proof system that only consists of additive cut and identity, you will see that you can prove the additive version, but you can't have the same proof for the multiplicative version. The proof will fail. You'll need to add weakening in order to make it work. So there's kind of an incompatibility problem with different additive and multiplicative formulations. If you did, this is the reduction step of a harmony proof for this kind of minimal calculus. If in the same minimal calculus you did then an identity proof, and then were to look at another parameter of the derivability relation, not only, you know, transitivity, monotonicity, and so on, but we're also looking at the how much space have we got on each side of the sequence symbol, and we look at the restrictions, right? Naturally, this proof will need at least two instances on the left, on the right, the dual interstinstic case. For the interstinstic case, you would need these two instances on the left, right? So you would also have in the identity proof a difference of structural framework presumed. Is that clear so far? Kind of glossing over a few things. These general effects are described as codetermination effects. That's Bogdan Diche described those first in 2016. And they were kind of a puzzle to the logical pluralism community, because this is where the original results come from. And they say, okay, this is a problem for meaning invariant logical pluralism, because that's also where the active components criterion comes from. All right, but what does this tell us as proof theoretic semanticis? That's the question that I'm after. My proposal is, well, we see the active formulae alone don't seem to determine the use of our connectives in the operational rules, right? There are other aspects of our proof systems that determine how we're going to use them in proofs as soon as we leave this ultimately strong kind of vantage point and go a bit more substructural. And the question is just which ones, right? So my idea is, let's just measure which ones, right? All we need is a systematic measurement procedure. And the idea that I'm proposing for this is a methodology for proof theoretic semantics that I'm trying to propose is, well, first of all, we need a way of operationalizing use, right? We want to measure how we use things, so we've got to find a way of measuring use. And the way I say we can do this is just, let's look at the inferential behavior. That is at all of these syntactic instances and transformations of formulae that contain the connective we're interested in studying. So we're kind of tagging, when we're doing proofs, in our proofs, all of the connective containing expressions, right? And then relative to this independent variable, we vary the different parameters of the proof rules and then see which ones affect the inferential behavior and which ones stay constant under change. You know, you change the components, but the inferential behavior stays constant. Whatever changes it That's what determines use, right? And then based on that, we can define the kind of core of the proof rules that is actually the part of the proof rules that tells us the meaning of the operator. All right. How do we do that in practice? Well, we need a kind of data set to do the measurement process in, right? And for that, I use definability proofs. Definability proofs means harmony. I'm very happy with the very traditional Belknapian conception. We've just heard about it, conservativity and uniqueness of the connectives. So generate the data set with the original rule that you start off with. Tag all of your instances. Restrict your structural context by one parameter. Do the definability proofs again in the new context. Tag, see, has there been a change? If no, grand, continue. If yes, write down which parameter you've changed, because that was a meaning determining parameter. And you need to do it in a very systematic and structural way. You see this, offers itself easily to computational implementation. And then here comes the plot twist. You don't just do that for any proof, because it would be kind of a bottomless hole. But you have to restrict yourself to a certain set of proof environments. And specifically, I want to be as minimal as possible here. So instead of just looking at the rules RESTful style by looking at the active formulae, I'm actually looking at proofs, but I want to stay to the most minimally possible proofs, which means we just need enough that we can do proofs in the first place. In a lot of cases, I think that having cut and identity is a good choice for this. Why? Because identity is a leaf for your proof trees if you're in sequent calculus, right? And cut is the only thing that you, the only standard proof rule in a standard LK kind of calculi that you can have both sides of the sequent interact with each other, which is something you would want to deal with when you do harmony proofs, right? But if you have any other tool that serves as a leaf and as an interactive tool for your sides of sequence, that's perfectly fine. I'm completely pluralist about the choices you make for your testing environment. Just be consistent with it. This might be a bit confusing. So maybe let's tell you a little bit of a story that can maybe give you the feeling of the whole thing. So think of your connectives as animals, right? And you're all now zoologists. So you take out your binoculars, you're sitting in the rainforest, and you're observing the connectives. And sometimes you're interested in how the connective behaves in its full natural habitat, in its full logical habitat, right? You're interested in the way the connective interacts with other connectives that are playing out there, right? You're interested in how the connective interacts with its environment, right? This is what we're interested in when we're doing structural proof theory for the full calculus. But when we're interested in questions about the connective, what the connective is specifically, we might not want all of those confounding variables with all of the other structural properties of the environment, right? All of the other animals that are around, all of the animal-environment interactions. We rather want to take that animal, put it in an isolated laboratory context, and study its anatomy, study its behavior in isolation. And that's kind of the idea here. We create ourselves a minimal proof context as a kind of testing environment, just strong enough that the connective survives, right? We feed it, right? We give it water. We want to see some meaningful behavior. We don't just want to study a dead body. Bit dark. But we still want to keep it as minimal as possible, right? To see just as little of those confounders of the structural environment as is possible. And there are multiple ways of designing a testing environment, just like when you design experiments, right? Similarly here, you can have all kinds of minimal proof environments as long as you can do proofs, right? You need leaves, you need an interactive tool, something that works. All right. That's the story. So what do you get out of that? Well, firstly, you get an answer to your question, right? So you will get something like, well, your ifs are the same ifs if one is classical and the other one is intuitionistic. They're also the same ifs if one is classical and the other one is dual-intuitionistic. But wait, they're different ifs if one is intuitionistic and the other one's dual-intuitionistic. Something's fishy here, right? That doesn't seem to add up, right? That's a contradiction, isn't it? Well, let's be careful what we're talking about. Whoops, sorry. Think about the metaphor, right? Classical logic, intuitionistic logic, dual-intuitionistic logic. These are the four logical habitats that our connectives inhabit. But you can put the same connective into different proof environments. So when we're observing things like you have different ifs and the same ifs, you make assertions about the species of the connective at hand, right? About what the connective actually is. But there is not necessarily a problem that you have the same connective in two environments, but you have a clash in other environments. These are properties of the full derivability relations. These are properties of the structure beyond the meaning of the connectives that you get. So, the core takeaway is we can measure our if, and we can measure it independently from the proof system that it's used in. And out of that, you get a bunch of natural applications, things like you get a form of logical pluralism for free that is in the tradition of Paoli and Diche for the more philosophically minded people. You get this kind of notion of measurement. You get the calculus independence. And you also get a bunch of interesting results that seem to align very neatly with the way we think about things. Let me maybe try to show you a few results to make this a bit clearer, if we've got the time. I think we do. Let me just look at, so I'm going to show you a result table for all of the minimal structural properties measured in that way using the minimal structural context, which you always need to specify because it's relative to our measuring environment of multiplicative cut and identity. For all of the possible connectives that you can define, binary connectives without repetitions that you can define in two-sided sequence calculi. So that's kind of the full overview table. And then you see here specifically you need, what do you need? Do you need multiplicative or additive cut for the definability? Surprise, surprise. You're fine with additive, you need additive positioning, right? This is the additive positioning versus the multiplicative positioning. Surprise, surprise. The multiplicative rules need a pair of the two multiplicative positionings, and the additive pairs need the additive positionings. That seems to be quite straightforward. And then you get the properties of the derivability relation. So think of the sequence symbol as the turnstile. And so you can think of it as a derivability relation. The minimal derivability relation you can define that connective in this case, for instance, is a derivability relation between a formula and a set of at most cardinality 2. Or in this case, a formula and a set of at most cardinality 3, for instance. So you get this overview of the connectives, and the results seem to line up very neatly, right? The additive connectives here, for instance, compatible with minimal logic. That's what we define in minimal logic typically. These are the minimal logic connectives. Now we have a kind of etiological story, meaning theoretically for that. Or here, this is compatible with intuitionistic logic. And as it happens, right, these are the connectives you would also find in the natural habitat of intuitionistic logic. We've just got a meaning theoretical origin story for that. So it looks like a complex results table. It actually tracks very nicely. You can explain the different relations between the LL connectives and the intuitionistic ones, which are cross-definable, which ones aren't. You get a nice story of how there is a relationship between, so you will see that for the classical conditional, you've got two options of setting your minimal structural framework. Same for classical negation. You've got two options, and as it happens, one aspect of those options is compatible with dual-intuitionistic logic. The other aspect is compatible with intuitionistic logic. That's how you get this nice relation that you have aspects of the meaning of classical logic then contained in the meaning of intuitionistic and dual-intuitionistic logic, but those two have incompatible aspects of meaning, just like you would expect it from the way you use the calculi. So I think there's a bunch of interesting results. If you want to know more about this, obviously you've got to read a paper because there's a lot of nitty-gritty details and it's full of bureaucracy because it's proof theory, right? So there's a lot of bureaucracy to observe, which is why I love this so much. But I hope I could give you like a basic idea of why this might be a cool thing to be thinking about. And I'd be happy to hear your questions, comments, criticisms.
You like determine the identity, let's say, of rules in the context of like in the relation with certain, the presence or absence of certain structural properties.
So look at the minimal structural properties that you require to define those rules meaningfully, and that's how I establish the meaning identity between rules, yeah.
And to me, at least, some of these logics, like there's one more like factor to have into account, which is negation, right? Because maybe in, at least in natural deduction, all of these can have the same rule, let's say for conjunction or for the same rules for disjunction, but you take and add different like negation rules or falsum, let's say,
Yeah.
they I don't know, like they go different ways. So I don't know. It left me thinking like, how does negation like would come in place here?
So negation, you can tell a nice origin story in the same way you tell it for the conditional about negation, how you've got for dualistic and internistic negation, each aspects of negation that you also find with negation in classical logic, because you've got more versatility of definability. The way you do your definability proofs, you can do them two ways, but you can each do only one way in each of internistic and dualistic logic. If you take LJ and LDJ as your calculi, which doesn't have the falsum necessarily, you can still define them slightly differently by just tweaking the structural properties, because you've got everything made explicit. I don't really have a nice story for the zero place connectives, if you want to think of falsum and top that way yet, because they don't really satisfy a lot of the properties. They might, in a sense, be trivially definable, because you don't get this kind of classic harmony story. I also don't have a story for the quantifiers, really, because quantifiers are hard and kind of scary, but it would be nice to have one. But I think that will be a lot trickier. You might need to type some stuff, and then it gets technically quite demanding. Did that answer your question? So there is a little bit, there isn't everything, I can't make sense of everything, but there's a lot, and it tracks really nicely with the way we do logic, which I think might want to make us pursue this further, and it gives us nice stories, meaning theoretic stories.
I think that her question is really fantastic, because when you go to minimal logic, for example, you don't have that falsum. So, yeah, I don't see how you can...
You don't have any meaning compatibility of the notion of negation at all, of LK, like between minimal logic and all of the other logics in the LK family. So you just don't have any, that's all I just say. So the only thing I can talk about are these two. That's as far as I'm with minimal logic.
Oh, okay.
But it can tell a story why those two, and it can tell you a story why we can't, purely meaning theoretically, without talking about other properties involved. Only this kind of minimal use kind of thought experiment or actual experiment, depending what your conditions for an experiment are.
And this is really, I mean, you need a harmonical kind of things, right? You cannot put tonk there.
Yes, that's why I look at definability proofs as my data set, because that's kind of, I get this free house. That's why I've been dealing with localized, it's basically local harmony, cut inductivity, Steinberger would call it, that I'm working with, and then uniqueness.
Okay, but when you say harmony, other than cut elimination, because you were talking about normalization or cut reduction, right?
So I talk about cut elimination in a localized setting, because I only add this to the minimal derivability relation, so it's automatically localized cut elimination. And then I've got interderivability proofs. So I get the two Belknapian criteria, conservativity and uniqueness, out of that. I would like to play with other notions of harmony, invertibility notions, but I want to be a bit more liberal, and I think the Belknapian notion has the potential to be more liberal.
Just for me to know if I'm on the same page as you are. So for me, harmony involves cut elimination, but also the possibility of having atomic axioms. So this is the other one you're talking about? Whatever that I don't know. Is it?
Uniqueness just means that you have exactly one that has the inferential function, exactly one connective that has the inferential function of the one you're trying to define in the extended calculus.
Okay. So then my question is going to make sense. So how about, because there are connectives like tonk that they do not have cut elimination. There are connectives that they do have cut elimination, but they don't have this other one. So you don't...
Yeah, there are some people want to pose further constraints, and then you get into the whole harmony literature, which is...
I think I sent to you the paper of don't work or not.
I think we talked about it. I don't know if you've sent it, but we can talk about it again. There are a bunch of notions of harmony which are interesting for this. And I'm working on a paper. Actually, Stephen Reed has given me a bit of advice on like what I should look into, because there is so much in the literature out there, and he's done a lot of work. One notion that I'm extra interested in, which is brand new, is Hannes Leitgeb has a new conception of of definability, kind of a notion of harmony, where he thinks about it in terms of classic theory of definition, classical mathematical theory of definitions, where you take the connective rules, you convert them into statements in monadic second-order logic, and then prove that they satisfy the criteria for a traditional theory of definitions. That might be something applicable here. It's not quite ready yet, but it's a really interesting notion. So I think what I want to do is I want to explore a bunch of notions of harmony and how they would play into that project. But I do think that the Bell-Napier notion does a lot of work already, and it might actually be a really good notion to get this off the ground. Because one of my desiderata is I want to be maximally liberal. I want to be able to, you know, if you have logical monists, right, who only want to deal with one logic, that they can give semantics. But also for the radical pluralist, I want to be able to give semantics, just maximally ecumenical.
Oh. Now you got my heart.
Thank you very much.
Thank you.